Hello students, welcome to the electrical engineering channel. So from the previous lecture we have started the section of synchronous motors, and in the previous lecture we discussed the operation, construction and working of synchronous motors. And we have also discussed already the phasor diagrams of various quantities associated with the synchronous motors. So now we will discuss the cases of different excitation of the synchronous motor, and excitation actually corresponds to the current which is applied at the rotor side or at the rotor winding. So when we increase the rotor current, we will say that we have increased the excitation and vice versa. So when we increase the excitation at the rotor side, the back EMF will be increased, and the magnitude of the back EMF will increase, but the angle of the back EMF with the voltage axis will be same. So if we want to change the angle between the back EMF and the voltage vector, which is alpha, and this angle is also called load angle. If we want to change this angle, keeping the magnitude of the back EMF constant, then we have to change the mechanical load. Okay, so I will repeat again. If we want to increase or vary the magnitude of the back EMF or the length of this back EMF vector, we have to play with the excitation. And if we want to keep this magnitude constant, and if we want to vary the load angle, then we have to keep the excitation constant, but we will have to vary the load. So in this case, we are discussing the synchronous motor with the various different excitations, but at constant load. So in that case, the magnitude of this EB vector will vary. So in the first case, suppose we have kept EB or back EMF equal to the applied voltage. So in this case, you can see that the length of this EB vector is exactly equal to the length of this voltage vector. So in this case, we have to deduce the other vectors, for example, the IA vector and the reactance voltage vector, and we will have to check the nature of the power factor. So under in this case, the back EMF is equal to the applied voltage. So this is EB, and we have to produce or we have to place this EB vector at the top of this voltage vector. So this is EB, and EB dash will be anti-parallel vector placed over here, and this ER vector will start from the tail of this voltage vector to the tail of this EB dash vector. So by making such a triangle, we will say that V is equal to ER plus EB. So the equation which we already discussed in the previous lecture is satisfied. So V is equal to EB plus ER. So this is the ER vector, this is the EB dash vector, and as I already said in the previous lecture, that this IA vector will be at almost 90 degrees with this ER vector. Now this ER vector is slightly tilted towards right from the y-axis. So it means this armature current vector will also be tilted downward from this voltage vector, because this IA vector and ER vectors, they are almost at 90 degrees with each other. So this is the orientation of this armature current vector, and here we can see this armature current is lagging behind this voltage vector by the angle phi. So we have obtained a lagging power factor in this case when we have such an excitation to result back EMF equal to the applied voltage. Now in the second case, we have slightly reduced the excitation, and as a result this back EMF is also reduced, and we can see that the length of this back EMF vector is slightly smaller than the length of this applied voltage vector. So this is EB, and EB dash will come over here, and this will become ER from the tail of the voltage vector to the tail of the back EMF vector, and IA will come over here. So again IA is lagging behind the voltage vector, so we will get again a lagging power factor case. So if we keep EB greater than V, so if we have increased the excitation, then EB vector will be greater than the applied voltage vector. So this is EB, and this will become EB dash vector, which is anti-parallel with this EB vector, and the tail of this voltage vector will be joined with the tail of this EB dash vector by means of this another vector which is called ER. So now ER has shifted towards left from the y-axis. So as a result, the IA vector will also come on top of the voltage vector. So in this case, IA is leading the voltage vector by 5 degrees. So if we increase the excitation in synchronous motors, we will get a leading power factor case. So if we want to get a unity power factor scenario with a synchronous motor, then we have to keep this back EMF vector slightly greater than this applied voltage vector. So we will keep such an excitation which will cause slightly greater back EMF vector as compared to the applied voltage vector. So this is EB, and EB dash again will be the anti-parallel vector over here, and the ER vector will start from the tail of this voltage vector to the tail of this EB dash vector. So this is ER, and IA is almost at 90 degrees with this ER vector. So IA will be in phase with this voltage vector. So in such a case, when we have slightly greater back EMF vector as compared to the applied voltage vector, we will get a unity power factor case. So now we will have to derive the expressions for the back EMF and the load angle by using these phasor diagrams. So in the first case, we will discuss the lagging power factor case. So when we have a lagging power factor scenario, then we will get such a phasor representation, and this is the back EMF vector EB, and EB will be equal to the sum of this vector and this vector. Now the vector from O to A is the voltage vector. If we subtract this vector OB from this whole voltage vector, we will get this AB vector. So V minus OB plus BC will give us the back EMF vector. So this now the question is that what is the value of this OB vector? So this OB vector will be calculated by resolving this reactance voltage or ER into two components. This is the horizontal component and this is the vertical component, and the angle between this ER and this OB vector is theta minus phi. So this whole angle is theta, this is phi. So this is theta minus phi. So this vector will be equal to ER cos theta minus phi, and this vector will be ER sin theta minus phi. So this EB will be equal to V minus ER cos theta minus phi plus ER sin theta minus phi, and we will put a J or iota over here because this is the vertical component. So the magnitude of this EB or the magnitude of this AC will be given by taking the square of this x component plus the square of this y component and then taking the under root. Similarly, the load angle alpha will be given by BC over AB. So tangent inverse BC over AB, and it will be equal to tangent inverse ER sin theta minus phi divided by V minus ER cos theta minus phi, and ER is equal to IAZS. So this will be giving us the load angle for the lagging power factor case. So for the case of a leading power factor, so if we have a leading power factor scenario, then we will get this phasor diagram, and this phasor diagram corresponds to the leading power factor case. So in this case, this is EB, and EB is equal to AC, and it will be equal to AB plus BC, and AB is equal to V. So OA is V, and OB is another vector which will be obtained by resolving this ER into two components. So this is ER and this is ER cosine component, this is ER sine component, and this we have to first calculate the angle between this ER and this horizontal component. So this angle is phi, this angle is theta, and this total angle is 180 degrees. So if I subtract theta plus phi from this 180, I will get this angle. So ER cosine 180 minus theta plus phi is the horizontal component, and the vertical component is ER sine 180 minus theta plus phi. So in this way, I can calculate this EB. So EB will be equal to V plus ER cos 180 minus theta plus phi plus JIA ZS or IAZS is ER sine 180 minus eta plus phi, and alpha is the angle, is the load angle, and it is equal to this term tangent inverse this term divided by this whole term, and this is the load angle alpha. So I think it is very easy to calculate for the leading power factor case. And in unity power factor case, this IA and voltage will be in phase, and we will get such a phasor representation. So EB in this case will be equal to AB plus BC, and AB is actually equal to V minus IARA. So V minus IARA plus this component is JIAXS. So EB will be equal to V minus IARA plus JIAXS, and the magnitude of EB can be calculated by taking the square of this real part plus square of this imaginary part and then the under root. So alpha is equal to tangent inverse imaginary part divided by the real part. So these are the three cases in which we can calculate differently the back EMF and the load angle. And finally, we will discuss the case of increased load with constant excitation. So in this case, we are varying the load, but we are keeping the excitation constant. So here you can see that the load is small, so angle alpha 1 is small, and this is the back EMF, and this is the anti-parallel back EMF vector, this is the applied voltage vector, and this is the ER vector, and here we have a 90-degree angle between ER and I, and this is the phi angle between V and I. Now, if we have increased the mechanical load, this load angle will increase, and EB vector will orient in this direction. So this angle has increased now, but the magnitude of this back EMF vector is same. So EB2 is here, so we can reorient, or we can place this EB vector over here, and both these vectors are parallel, and ER will be actually starting from the tail of this voltage vector to the tail of this back EMF vector. So this will be the new ER, and now ER has shifted towards right, so this IA vector will also be shifted downward. So this angle phi 2 will increase as a result of this increased load. So when we increase the load, we can see that this IA vector has increased. So IA2 is greater than IA1. Similarly, this angle phi 2 has also increased. It means now we will get smaller power factor as a result of increased load, and this load angle has also increased as a result of increased load, and this reactance voltage vector is also increased. Here the ER vector was, the magnitude of this ER vector was smaller, and here the magnitude of this ER vector has increased. So when we increase the load, mechanical load of the synchronous motor, the stator current also increases. This angle phi corresponding to the power factor also increases, load angle also increases, and this reactance voltage also increases. And now if we increase both the excitation and the load, then we can see that this load angle has increased, this back EMF has also increased, this reactance voltage has also increased if we increase both the excitation and the load, and this armature current has also increased, and this angle phi all has also increased. So the new power factor will be less when we increase both the excitation and the load. So that is all about our today's lecture, and I hope you have understood different scenarios of the phasor diagrams under different excitation and different loading conditions. So for watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.